Welcome back to the deep dive. Today, we're taking you on a journey through probably the biggest scientific revolution, certainly of the last 150 years.
Yeah, it's quite a story.
Our mission, really, is to unpack how 20th century physicists, Planck, Einstein, those quantum pioneers just completely dismantled the elegant, predictable 19th century view of the universe.
The old clockwork universe idea.
Exactly.
Hmm.
And replaced it with something, well, frankly, weird, probabilistic, uncertain.
To really get the shock of it, you have to see where things stood before. The intellectual starting line, the whole scientific world was built on Isaac Newton's laws.
That perfect clockwork mechanism.
Pretty much. But even Newton had this awkward bit, gravity.
Yeah.
He had to describe it as action at a distance.
Right, this instantaneous force somehow reaching across space. He couldn't say how, just that it worked.
Exactly. And that idea, that instant action, it didn't sit right. Eventually, the concept of fields sort of fixed that.
Fields, like magnetic fields.
Yes, and electric fields. James Clerk Maxwell, back in 1864, she pulled it all together with electromagnetism, showed these fields spread out, propagate, at the speed of light.
Which put a speed limit on the universe.
It did. Definitely no instant action. So classical physics, governed by these fields, looked deterministic, beautiful. Complete, really.
Looked complete, except it wasn't quite, was it? There were a couple of, well, initially minor problems that just blew up.
Yeah, two little cracks in the foundation.
One was about how hot things glowed, emitted light. The other was about this thing called the ether that light was supposed to travel through, but nobody could find it.
Let's start with that first crack then, the birth of the quantum.
Okay.
Max Planck, late 1800s. His problem was driven by experiments looking at black body radiation.
The light spectrum you get from hot objects?
Right. And the classical theory, the Rayleigh-Jeans law, it sounded great on paper, but it was just totally wrong compared to the real-world data.
What did it predict, that classical idea, if you followed it logically?
It predicted something they called the ultraviolet catastrophe. Basically, infinite energy.
Infinite. How?
The math said that as you looked at higher and higher frequencies of light towards the ultraviolet end, the energy radiated should just shoot up to infinity. An infinite amount of energy from a normal, finite object.
Which is just absurd. Physically impossible.
Completely. The theory kind of worked okay for low frequencies like infrared, but failed catastrophically for the higher ones.
So Planck steps in. What did he do? This was around 1900.
1900, yeah. He did something really bold, almost desperate. To make the math fit the experiments, he introduced this peculiar assumption.
Which was?
That atoms couldn't just absorb or emit energy continuously in any amount. They could only do it in these discrete little bundles, packets. He called them quanta.
And I always find this a bit fascinating. He didn't actually believe in it, did he? He thought it was just a mathematical trick.
Absolutely. He was deeply uncomfortable with it. Quantization, these indivisible energy units, it messed with the smooth, continuous classical world he knew. He called it an act of despair.
Hoping it would just go away.
Yeah, he hoped his new constant, H. Planck's constant, would eventually be proven to be zero, which would mean, no quantization after all, back to the old ways.
But it didn't turn out to be zero. The math needed it. It stuck.
It stuck, firmly entrenched.
So what does that constant H fundamentally mean for how the universe works?
It means energy and action aren't infinitely divisible. There's a minimum packet size.
Yeah.
H defines the granularity, the ultimate resolution of reality, you could say.
And it shows up everywhere in quantum mechanics.
Everywhere. The Schrödinger equation, Heisenberg's uncertainty principle,
Yeah.
it's a fundamental constant of the quantum world. It told us the universe, at its tiniest scale, isn't smooth, it's lumpy.
Okay, so while Planck is sort of reluctantly kicking off the quantum idea, there's this young guy, Albert Einstein, tearing down classical ideas about space and time.
Yeah, Einstein. His Annus Mirabilis, the miracle year, 1905. Just incredible.
He was obviously brilliant from a young age, right? Mastering calculus super early.
Oh, yeah. Calculus by 14, apparently. In 1905, bam, 4 huge papers. One of them was special relativity, and that tackled the other big problem, the ether.
Ah, yes, the ether. This, invisible substance everyone thought filled space, the medium for light waves.
That's the one. If light's a wave, it needs something to wave in. That was the logic.
But Einstein said...
He said it was unnecessary, superfluous. The core idea of special relativity is that the speed of light is constant for everyone, no matter how they're moving. The ether just wasn't needed to explain that.
And there was experimental evidence backing this up already.
There was, crucially, the Michelson-Morley experiment from 1887. They tried really hard to detect this ether wind, the effect of Earth moving through the ether.
And they found
Nothing. Nothing, a null result. No difference in light speed, no matter the direction. It was a huge headache for classical physics.
a real embarrassment.
It's a serious embarrassment, yeah.
Yeah.
Einstein later said his theory was a kind of redemption because it explained that null results so naturally. Space and time themselves aren't fixed. They adjust depending on your motion.
Moving clocks slow down, moving things shrink a bit.
In the direction of motion, yes, relative to a stationary observer.
And the most famous result of all this is, of course, MMC, everyone knows the equation, usually explained as mass turning into energy.
Right, like in nuclear bombs or reactors.
Mm-hmm.
But the sources we looked at emphasize it's deeper than that, yeah.
How so?
It's really about equivalence. Energy is mass. Mass is energy. Any kind of energy, motion, potential energy, heat, it all contributes to an object's mass. It's part of its inertia.
Wait, hang on. So the energy that holds, say, an atom together, that actually affects its mass?
It absolutely does.
Yeah.
This blows the classical idea of fixed matter right out of the water. Think about a hydrogen atom, just a proton and an electron.
Okay.
If you weigh the proton, weigh the electron, add those masses up, the actual hydrogen atom weighs less than that sum.
Less.
Because the energy binding them together, the potential energy, is negative.
Mm-hmm.
And since easy we court, that negative energy means less mass for the whole system.
Wow. So binding energy reduces mass.
Exactly. Energy stored in bonds, positive or negative, it shows up on the scales as mass.
Line bending. And by 1915, Einstein wasn't done. He expanded this into general relativity.
Bringing gravity into it, not as a force, but as the curvature of space-time itself, which leads to things like black holes, gravitational lensing.
Like those Einstein rings you see in space telescope images.
Precisely. But what's fascinating is how Einstein's other big 1905 idea, the one explaining the photoelectric effect, actually pushed us straight back into the quantum weirdness Planck had started.
That was the idea that light isn't just a wave, but also particles. Photons?
Yes. He proposed light consists of these localized particles of photons, an idea that was deeply unpopular at first.
Really? Even among the quantum guys?
Oh, yeah. Planck himself, Niels Bohr giants of the field, they hated the photon idea initially. They were all in on light being purely a wave.
But that idea that things can be both particles and waves, that's kind of the heart of quantum mechanics, isn't it?
It absolutely is. Particle-wave duality. It's what makes quantum mechanics so counterintuitive.
The classic example being the double-slit experiment. Even if you fire particles like photons or electrons one by one,
They still build up an interference pattern over time, as if each particle somehow went through both slits at once, like a wave.
which is just bizarre. How do you even describe that mathematically?
That led to the concept of the wave function. It's the mathematical description, but it's not describing a physical wave like water. It's more like a wave of possibility.
A wave or possibility?
Yeah, it represents a probability distribution. All the possible places the particle could be found or all the possible states it could be in, all superimposed together.
So it doesn't have a definite position until you actually look, until you measure it.
That's the standard interpretation, yes, the Copenhagen interpretation. When you measure it, the wave function collapses, and poof, you get a single definite result.
And describing this mathematically, there were different approaches.
Right. You had Erwin Schrödinger and Paul Dirac developing wave mechanics. That's often what you see in textbooks because it's a bit easier to visualize. And then Werner Heisenberg developed matrix mechanics. Different math, but equivalent results.
Heisenberg. He also gave us the uncertainty principle in 1927, maybe the most famous part of quantum theory.
Yes, the uncertainty principle. It says you fundamentally cannot know both the precise position and the precise momentum, basically velocity of a particle at the same time.
And crucially, this isn't just because our measuring instruments aren't good enough.
No, absolutely not. That's the key point. It's not an equipment limitation. It's baked into the fabric of reality. The universe itself imposes a limit. The more precisely you pin down one property, the inherently fuzzier the other one becomes. Uncertainty is fundamental.
And that idea that the universe is fundamentally fuzzy or probabilistic, that sparked a huge philosophical fight, didn't it? The Bohr-Einstein debates.
Oh, it was epic. A real clash of titans over the nature of reality itself. Does the universe exist in a definite state, even when we're not looking?
Bohr, leading the Copenhagen view, said,
Bohr basically said it's meaningless to talk about properties like position before you measure them. Observation creates the reality. in a sense.
While Einstein championed realism.
Right. Einstein hated the probabilistic nature of it. He believed everything must have definite properties, whether we measure them or not. They must be determined by some underlying local hidden variables we just hadn't found yet. That's when he made his famous remark.
God does not play dice with the universe.
Exactly. He couldn't accept that reality was fundamentally based on chance.
And this whole debate crystallized around entanglement, right? Which is arguably the weirdest quantum phenomenon of all.
It really is. Entanglement. You have two particles linked in a special way, sharing a single wave function.
So they're like one system, even if they fly far apart.
Yes. And if you measure a property of one particle, say, its spin, you instantly know the corresponding property of the other particle, no matter how far away it is. Instantly.
Faster than light. That's what bothered Einstein so much.
That's what he called spooky action at a distance. It seemed to violate locality, the idea that influences can't travel faster than light. It looked like forbidden communication.
So how did they resolve this? Or did they?
For decades, it was mostly philosophy. But then, in 1964, John Stuart Bell came up with a brilliant theoretical test, Bell's theorem and Bell's inequalities.
What did they test?
They set mathematical limits on the correlations you could expect between measurements on entangled particles if Einstein's local realism was true. If reality was local and particles had definite properties before measurement, the correlations couldn't exceed a certain level.
And then people did the experiments.
Yes, starting in the 70s and 80s, and getting more precise ever since.
And the verdict.
The experiments consistently violate Bell's inequalities. By a lot. Meaning, you have to give up something Einstein held dear. Local realism is out. You either have to abandon realism, the idea that properties are definite before measurement, which is the standard Copenhagen view, or you have to abandon locality, meaning you accept faster than light influences or connections.
Wow. So the universe really is spooky. It's either not real until looked at, or things are connected instantly across space.
Our current understanding points towards non-locality being the feature we have to accept. Entanglement strongly suggests the universe isn't strictly local.
Okay, so this fundamental weirdness, this non-locality, it carries through into how we understand particles themselves today with quantum field theory or QFT.
It does. QFT is the modern framework, the synthesis that marries quantum mechanics with Einstein's special relativity. It's crucial.
And the big shift with QFT is how we think about particles. They aren't little balls anymore.
Not fundamentally. In QFT, the basic components of reality are fields, quantum fields, permeating all of space-time.
Like the electromagnetic field.
Exactly. There's an electron field, a quark field, and so on. And particles, like electrons or photons, are just excitations, ripples, or localized vibrations in their respective fields.
So a particle is like a wave crust moving across the field.
That's a decent analogy, yes. And this view neatly explains how particles can be created and destroyed.
How so?
Well, if you add enough energy to a field, say the electromagnetic field, you can excite it enough to create a photon particle. Or you can have an electron and its antiparticle, a positron, annihilate their field excitations, cancel out, releasing energy into, say, the photon field. You're just moving energy between fields.
That makes sense. So QFT was a huge success, unifying relativity and quantum mechanics for particles. But it ran into a big problem, the mass crisis.
A major hurdle, yes. The theories within QFT that describe the weak nuclear force, one of the fundamental forces they initially predicted that the particles carrying that force, the W and Z bosons, should have zero mass, like the photon.
But experiments showed they do have mass. A lot of mass.
A lot of mass, yes. Very heavy particles. This was a massive contradiction, a potential failure of the whole standard model of particle physics.
Okay, so how did they fix it? This is where Peter Higgs comes in.
This is the Higgs mechanism. Peter Higgs and others around the same time proposed a solution. Another quantum field.
Yet another field.
Yes, one that permeates all of space, even the vacuum. The Higgs field.
And this field is special how?
The idea is that particles don't inherently have mass. They acquire mass by interacting with this Higgs field. It happened very early on, a fraction of a second after the Big Bang when the field turned on.
So it's like moving through treacle. Some particles interact a lot with the field, feel a lot of drag, and that's what we perceive as mass.
That's a very common analogy, yeah. More interaction means more inertia, which means more mass. Particles like the photon don't interact with the Higgs field at all, so they remain massless.
And the Higgs boson, that's the particle associated with this field.
Exactly. Just like the photon is the excitation of the electromagnetic field, the Higgs boson is the excitation of the Higgs field. Finding the Higgs boson in 2012, confirmed at CERN, was the proof that this mechanism, this field, is real. It was the final missing piece of the Standard Model.
Filling that gap in understanding mass, though, it got that slightly controversial nickname, didn't it? The God particle.
Yeah, that nickname. Leon Letterman used it for a book title, partly as a joke, partly because it was so crucial and so hard to find. But many scientists, including Peter Higgs himself, who's an atheist, really dislike it.
Find it misleading, sensational.
Pretty much. It explains more than it does. It explains the mechanism of mass acquisition within the Standard Model, not the ultimate origin of everything.
Right. It solves the mass puzzle within the existing framework.
Correct. But still, it completes this incredible century-long narrative. We started with Newton's clockwork, deterministic universe. Maxwell added fields propagating at light speed. Then Planck introduced Quanta out of desperation.
Einstein reshaped space and time, linked mass and energy, but also seeded quantum mechanics with the photon.
Then came the full quantum theory wave functions. Uncertainty. Entanglement shattering classical intuition. Bohr and Einstein battled over reality itself. Bell's theorem forced a choice, leaning towards non-locality.
And finally, QFT unified particles and fields, with the Higgs mechanism explaining mass. From clockwork certainty to, well, quantum fuzziness and spooky connections.
It's a completely different universe than the one physicists imagined in, say, 1890.
So pulling it all together, what's the deepest takeaway here? If we link QFT back to Heisenberg's uncertainty principle, what does that imply about reality itself?
Well, the uncertainty principle isn't just about measurement limits. It has real physical consequences. It allows for tiny fluctuations in energy for brief moments.
The borrowing energy from the vacuum idea.
Exactly. Virtual particles can pop into existence from seemingly empty space, borrowing energy, and as long as they disappear again within a time dictated by the uncertainty relation, QO2. They exist on borrowed time and energy. Now, think about the entire universe. There's a hypothesis, still debated, but plausible, that the universe is closed in terms of energy.
Meaning the total energy is zero. The positive energy of all the matter and radiation is perfectly canceled out by the negative energy of gravity holding it all together.
Precisely. If the total energy budget of the universe is exactly zero.
Then, wait, does that mean the whole universe could be like a virtual particle?
That's the mind-bending extrapolation. If the net energy is zero, then perhaps the entire universe could have arisen from a quantum fluctuation in nothing, a vacuum state, just like a virtual particle, without violating energy conservation overall.
So the foundation of everything might be just quantum uncertainty allowing existence from non-existence.
It's a profound speculative idea, but it follows directly from the physics we've been discussing. It suggests that the very existence of the cosmos might be the ultimate demonstration of quantum uncertainty. The universe itself might be fundamentally uncertain at its core,